So the idea of Starship is to disrupt last mile delivery with automation and robotics. So it was founded in 2014 by some of Skype co-founders, Ahti Heinla and Janus Fries. And first year it was kind of in stealth mode, doing prototype development, and for the last 2 years we kind of came out of stealth mode and have been doing real commercial applications of our technology. So the delivery industry is huge, especially in the EU and US. There are billions of packages delivered every year. Probably everybody in this audience ordered something online, had something delivered by like UPS or DHL, or ordered some food online and had it delivered. And last mile delivery is probably the least efficient part of the whole kind of delivery industry, because if you're transporting goods from between cities, it can be like containers and like planes and railways and trucks. But for the last mile it usually involves somebody driving around and handing packages one by one. And if you want to receive your package in some specific time, then it probably costs more money. People spend lots of time on groceries shopping and on waiting for packages. So applying robotics and automation would make it less expensive, more convenient. It also would be more energy efficient. So our mission is to build most efficient on-demand delivery service, where you can just press a button on your phone and have anything delivered to your home at the time which is convenient for you. So how has it worked so far? During last 2 years, we have grown to 200 employees. We have more than 100 robots operating in like 5 countries and even more cities. We're operating in London, in US, in Germany, in Switzerland. We're also partnering, so we are providing a delivery service. We're actually not a robotics company, we are a delivery company. And we are partnering with companies like Swiss Post and Domino's and Postmates and Just Eat in UK. And these large companies who are leaders in their fields of food delivery and parcel delivery are really eager to partner with us, because they see that robotics, AI, and automation is the future, and they have to jump on this wagon. So we've been driving for the last 2 years, and we have driven 100,000 kilometers on sidewalks of the cities like London and Washington and Hamburg. And so far, like having done so much testing, it has proven to be a viable idea and a really efficient way to deliver stuff. When we started, when the company was started, this idea of sidewalk delivery robot was really strange. Nobody was really doing it. And after we came out of stealth, it looks like every month some competitor pops up with a similar product. So there is a whole range of robots that are created for driving on sidewalks. On one side of the spectrum, there are like really simple robots like KiwiBot, which in its first iteration was something like a box on wheels with a smartphone attached to it. So this makes it very cheap, but also less safe and less applicable to a wide range of environments. Like further on the spectrum of complexity of the robots, we have Starship, and we have this Gita robot. And these robots are a bit more complex. They have more sensors. They are built more solidly, and this looks like a golden spot for delivery robots. And on the even further on the scale of complexity and size, there are these robots by Dispatch and Marble. They're quite large. They weigh more than 100 kilograms. and they have lots of sensors like lidars, so they're closer to something like self-driving cars. Well, we believe that this level of complexity and cost of the robot is not really needed for deliveries, and this is an overkill. But well, time will tell probably. Just an overview of the specs of our robot. It's not too large and not too small. It has a basket inside of it. And this basket is large enough to carry most of the packages. It can carry some food delivered to you. It can carry a pizza or some grocery bags. It drives not too fast at pedestrian speeds, so it can coexist with pedestrians on sidewalks. And it carries something like 10 kilograms. Inside of it, there is an embedded computer, which is NVIDIA's Tegra board. It uses cameras and computer vision to localize it in space and combining it with GPS. It drives autonomously, but it doesn't really have to be autonomous 100% of the time. When some unusual situation occurs, it can, operator can take over and control it via internet. So it can be 99% autonomous with people controlling them 1% of the time. And this means that one operator can control 100 of these robots over the internet simultaneously. So most of the time they're driving on its own autonomously, and sometimes people take over. This is a view of the control panel of the robot. As you can see, there are cameras, which full 360 view of everything around. Also, operators have access to controlling speed of the robot. They can show it where to go. Robots also know where the sidewalks are, where the road crossings are, and so on. So robots most of the time are connected with this video feed via the internet. We have driven during last 2 years 100,000 kilometers, 60,000 miles, and as you can see, the growth is almost exponential. And this growth in driving length also means growth in other exponential growth in other parameters as well, like number of robots and number of deliveries that we make. But it also means the same growth in amount of data that we collect. So this line here is the size of the data that we collect, and right now we have 500 terabytes. This data is all of the data from robot sensors, which is collected and gathered continuously. It's also some of the videos from the robots. For privacy reasons, we are of course not collecting videos all the time, but in some cases, for some time, we store videos, low-resolution videos of the robot's view. And also in some unusual situations, we save a bit higher resolution videos. We still, for privacy reasons, have to obfuscate and remove people from these images, and we don't store these videos and images for too long. But storing this data allows us to analyze any possible incidents and any unusual situations, and continuously improve our algorithms to make our robots even more autonomous and even more safe. So having all this data has lots of benefits. We try to be data-driven in our operation and in our system development. So, for example, we can, in our maintenance and mechanics development, we try to monitor robots' parameters all the time and be data-driven in this case. So this is an example of motor energy consumption over time. And as you can see here, we can see that, for example, one tire was broken, and if after it's fixed, the energy consumption gets back to the normal level. So we can predict maintenance events, and like we can also fix all the possible issues in time. Another application is routing of the robot on the streets. So the task of the robot is to go from point A to point B, so for example, from some restaurant to your home where you ordered your food. And in this case, there is a whole range of possibilities how robot can drive there. And we have to consider all the factors in efficiency of this route. For example, we would rather choose streets that are less busy, that have less cars and people on them for safety reasons. Or, for example, during the night, we would probably choose streets that have better illumination and that are less dark. Some streets might be more dangerous, like more shady neighborhoods, or some streets can have better pavement. So we can use all of this data combined with maps data, which we can pull from OpenStreetMaps. And we can use all of this data to really make decisions about routing, which improves both safety and efficiency. Now, I personally work on computer vision, so I can talk more about computer vision and perception of the robot, because this is the main, probably the main source of robots' actions, and the most important thing which allows robot to efficiently navigate in space. So most of the information comes from cameras. Here you can see that we have lots of cameras which give us a 360 view of the robot. This is like view with robot eyes. This is a panoramic image, 360 view, typical road crossings, some people, some cars. Cameras are used for obstacle detection and for visual localization. And for like constant monitoring of possible dangerous or unusual situations. Also, apart from cameras, we have other sensors like radars, ultrasonic sensors, gyroscopes, accelerometers, and so on. And all of this sensing information has to be combined together in a perception system. As for computer vision, well, usually in computer vision, it's split into like low-level, mid-level, and high-level visual processing, a bit similar to how human brains actually process visual information. So we have to implement in our software all of these levels and components in-house. For like having better control over software and for higher efficiency. So on low level, we have to actually do image acquisition from 9 cameras, which is not completely trivial. On higher level, we are doing stereo processing. So we have 3 stereo pairs, which gives us 3D view of the street surrounding robot. We also do features and edges and lines extraction for visual localization in the world. And on higher level, we do object detections of objects like cars and people and traffic lights. So for visual localization, we use the main kind of feature that we use for visual localization is straight line segments. Here you see a view where some lines were detected in the environment. And here red lines are the lines that are stored in a map. And purple lines are the maps that are detected. And if we match lines that are stored and that are detected, by matching it, we can actually localize the robot on the map. So if you think of it in any kind of urban or suburban environments, there are lots of straight lines. So this is really a good feature because it's usually some kind of unique pattern that can be used to actually localize in space. In combination with GPS, it gives us localization accuracy which is within several centimeters. We really do need this high localization accuracy because some urban sidewalks are really really narrow, and we need to know that we are really on exact correct part of the sidewalk. So we need to know exactly where we are. Usually in some other visual localization systems, point-based features are used, but we are using lines because, well, one reason is efficiency. They are more sparse, and another reason is that they are also present in untextured environment, so it really works in a wide range of environments. We also don't try to do simultaneous localization and mapping. We do mapping and localization separately. So so a robot can drive around in some neighborhood once on manual control, and then after that it will be able to localize itself and drive around autonomously. Another application of computer vision is obstacle detection. So for obstacle detection, we use a combination of stereo and ultrasonic sensors. It's really a complementary set of sensors. Here in red, you can see a range of, this is a top-down view of a robot, and here in red, it's a range of stereo sensors, and this blue is a range of ultrasonic sensors. So for farther objects, we use stereos. For closer, we use ultrasonics. Ultrasonics are actually similar to the sensors that are on cars for parking. And here you can see an illustration of the robot's 3D view of the world. There are some cars, some fences. This is the legs of some person that is standing in front. So having this kind of 3D point clouds allows us to detect obstacles really reliably and efficiently. And it's really easy to do it after we have this point cloud, because we can just build some kind of histogram and just say that, okay, so in this histogram, this space is filled, don't go that. It is well. It's still not so easy, because developing a stereo algorithm that can process information from 3 cameras in real time on computationally restricted hardware is still challenging. And also, there are lots of parameters that go into a stereo algorithm. Which algorithm to use, what thresholds to use, and what parameters to use, and so on. And we really try to be data-driven in computer vision and image processing algorithm development. That is, we have a data set of many thousands of cases of robot presenting with some obstacle, which we gather from a real world. And after doing any change to the algorithm, we can rerun this test on all of these test cases, and we can actually see how is this test really, is this change really good. And on the higher level, we have to do object detection. One of the applications is detecting like people and cars and traffic lights here. If we are talking about application, if we are talking about object detection in real world, it's often quite messy, not the same as you can see in some some conventional training data sets. For example, here you can see that this is really a car, and it's covered with some huge sun flare. And this is something that we have to work with. In real life, there are sun flares and raindrops, and sizes of the cars can be quite small. Like here, they can be partially occluded. They sometimes don't fit into camera view. They are blurred, and etc., etc. So this is quite a challenging problem. And of course, it's nice to be able to use deep learning for object detection. And in recent years, there's have been a huge advancement in performance of object detectors. One of the examples, so this chart shows accuracy versus speed for several object detection, neural network-based object detection algorithms. And as you can see, this kind of algorithm is both fast and accurate. So this is something that we decided to use. This algorithm is called YOLO, which is you only look once descripted, and it's so-called single-shot detection algorithm. So image is processed only once. On the input of the neural network, you have an image, and on the output, you have a set of detection boxes. You don't need to do any additional analysis of these boxes. So as you can see, this algorithm is quite fast. It works at 100 FPS, this seems like it's good enough. But the problem is that these tests are usually done on desktop GPUs. So although it is 100 FPS on desktop GPU, our embedded board that we use is around 10 to 20 times slower than powerful desktop GPU. So this means that we have something like 5 FPS on our Tegra board, 5 images per second. And it also, in addition to this, we are not processing only one image. We are processing at least 5 images to have a surround view around the robot. So this means that we actually can process 1 frame per second. And this also has to be combined with all the other processing that we are doing, like processing of stereos and detecting of features, and also doing like communication via internet and video streaming and so on and so on. So in this form, this algorithm is actually not useful. It's not fast enough. So we need to work on optimizing it. And how do we approach this? Well, we start with a neural network, with an algorithm that is good enough for us in terms of accuracy. And then we do as much simplification as possible. So for simplifying neural networks, we can remove layers, we can decrease image size, we can decrease number of convolution layers, and so on and so on. And with reducing of the network size, we also get a reduction of accuracy, but we also can have a significant reduction of processing time. So after we have this, after we have several versions of the neural network with different parameters in terms of accuracy and speed, then this becomes an issue of like system design and analysis of how good this network would be to achieve our targets in safety and autonomous driving capabilities. One more issue is that we have to also account for all the other issues, like, for example, image size. If we decrease a resolution of the input image for the neural network, then accuracy would decrease. But if you look at this chart shows a histogram of detection accuracy versus car size. So if we decrease resolution, then accuracy is only decreased for small cars. So for example, after we use a network with smaller input size, then this car here with blue will not be detected. So then we do additional analysis of how important it is to detect these faraway cars and so on. So this becomes more of a system design issue. This is an example of actually using computer vision to solve the problem of robot safety. In this case, as you can see, we are doing a road crossing here, so from this side of the road to this side of the road, and there are several cars here. Like this car is probably turning in here, and it might be dangerous for us, and this bus is probably passing, and this car is standing still. So we cannot make this decision just from a single image. So apart from this, we also need to do visual tracking. But so if we do visual tracking of this car, for example, then we can project it into 3D space, so we know direction towards this detected bounding boxes of the car, and we can also estimate distance to this car with the same depth cues that humans use, like perspective or side of the object. But this is not accurate enough because of all the inaccuracies of object detection and visual tracking. We cannot really accurately predict in all cases where the car is and what its speed. So apart from this, we also use, for each road crossings that we are doing, we use data from OpenStreetMap. to find out what are directions of the roads and which roads are potentially dangerous for us. So we know that the direction towards this car intersects with this road, and we can significantly improve accuracy of speed and position estimation. Still, there is ambiguity, because when we look at this car, it can be really on several possible roads in this direction. And to resolve this ambiguity, we once again use additional sensing data. For example, we use Doppler radars, which predict speeds of the cars. And, well, we put this all together into a probabilistic estimation algorithm, which gives us exact speeds and positions of cars, which we can then use to decide when to do a road crossing. So to summarize, our main priority is safety. So we are not trying to drive autonomously all the time. If it is, for example, on road crossings, usually people are monitoring and making a decision of when to cross. We sometimes, in areas that are more dangerous, we are not driving autonomously. We are driving under manual control. But getting new data about our performance and safety all the time allows us to improve it as well, and it has allowed us to drive for 100,000 kilometers without any accidents. And after some additional development and further testing and an improvement of our technology, we would be able to scale and put even more robots on the streets, like 10,000s, 100,000s, and eventually, hopefully, millions. So that's it, I guess.
Thank you.